Standard astrophysical models describe the origin of our solar system as a series of chaotic, random accidents. This nebular hypothesis assumes that over billions of years, planets built up through the unguided, stochastic accretion of space dust and gas. While this model accounts for how mass is distributed in bulk, it struggles to match the specific, highly ordered data found in the actual physical record of our planetary neighbors. Across every planetary tier, we observe a precise coupling between rotational dynamics and chemical complexity. This high degree of synchronization suggests the system is far more structured than a collection of random collisions would allow. Stochastic accretion explains why a planet has mass, but it cannot mathematically account for the self-similar stratification and predictable chemical sorting that defines the solar system's layers. If random chance cannot produce this level of architectural precision, then planetary formation must be governed by a deeper, deterministic physical structure. The infinite fractal descent, or IFD, provides that deterministic framework. It treats the transition from a diffuse molecular cloud to a planetary system as a governed phase transition rather than a sequence of collisions. Under this framework, the solar system folded inward. Energy cascaded from massive macroorbital scales down to the microscopic scale of molecular chemistry. This process is driven by a high-energy scalar field that condenses into localized matter vortices, which we eventually perceive as stars and planets. This inward fold occurs because the universe seeks to minimize information potential differences. When the density of information in a system exceeds its local processing capacity, the physical structure must reorganize into a more complex, efficient state to resolve the buildup. This self-referential reconstruction is a mechanism to avoid computational deadlocks, points where the system's own complexity would otherwise stall its evolution. The result is a mathematically inevitable descent into higher complexity. To initiate an IFD process, the starting environment must be geographically and chemically specific. Our system formed 4.6 billion years ago in a high-mass star-forming nursery located much closer to the galactic center than its current position. The symmetry-breaking event that triggered our system's collapse was a supernova from a blue-white giant star known as Kotlikwe. This explosion provided the seed data, a structural lattice of heavy elements like iron-60 and aluminum-26 that was injected directly into the protosolar cloud. Without this inherited informational density, the fractal descent would have terminated at the gaseous scale. The result would have been a sterile system of gas giants, lacking the material needed for solid terrestrial nodes. We can trace this origin through chemical tagging, a process of matching stellar DNA. Solar siblings like HD 162826 and HD 186302 share identical elemental ratios, confirming they were forged in the same initial data injection. The chemical makeup of our world is inherited data, specifically required to fuel the next structural phase of the inward fold. As the system collapsed, it established a fractal plane where a planet's rotational frequency was directly coupled to its mass. This coupling is governed by a universal constant, alpha equals 2/3. In granular rheology, this represents the exact balance between gravity pulling down and friction resisting flow. This same mathematics applies to our solar system. Planets scale their mass and energy according to this identical constant. Within this structure, the terrestrial planets of Tier 3 serve as fractal decay complexity nodes. These nodes experienced massive fractal friction from the Sun's gravitational well. This friction forced macroorbital energy to fold inward, compressing it into dense microchemical complexity. Every planetary position and mass is therefore deterministic, adhering to the universal fluid mathematics of friction and gravity. To refine the system further, it underwent a process of thermodynamic filtering, where elements were sorted as they transitioned through deep information potential wells. Transitions between these states occur only when the system crosses a fundamental threshold of energy change, known as delta phi. In the first phase, the primordial cloud remained a stable, high-entropy mass before any structural sorting began. Phase 2 utilized the frost line filter. Thermal gradients stripped inner nodes of light volatiles, purifying the core into dense silicates. In Phase 3, Jupiter and Saturn migrated. This delivered membrane data, water and carbon via cometary impacts, reintroducing complexity to the purified inner system. The catastrophic movement of the gas giants was a deterministic step required to prep the inner terrestrial nodes for the final fractal tier. The IFD framework identifies biological life as the mandated fourth tier of the solar system's structural descent. We can quantify this using assembly theory, which measures the shortest number of steps required to build a molecule from scratch. This chart plots assembly complexity against fractal depth. The dashed line at an assembly index of 15 represents the biological threshold. While stellar, planetary, and geological tiers fall below this, the biological tier is a massive leap in complexity, far exceeding the 15-step mark. The 15-step rule is a mathematical barrier. Molecules this complex, such as proteins or DNA, cannot form through random stochastic processes. They are physically impossible without a directed mechanism. Biology is the point where a planetary matter vortex becomes complex enough to process its own structural information through directed selection. Current astrophysical models describe spacetime as a fractal superfluid. This means the movement of any energy within that medium, including the electrical pulses of a human brain, must follow the same fluid dynamics seen at the cosmic scale. In this superfluid environment, neural activity can be modeled as wave vortexes. These operate as a microscopic continuation of the same rotational mechanics that collapsed the original protosolar cloud. Living systems represent a recursive saturation point, where the matter vortex begins modifying its own informational structure. Within this framework, humanity functions as the literal mechanism by which the universe continues its inward fractal descent. Mastering the 2/3 scaling constant and the delta phi threshold allows us to transition from observation to engineering. This knowledge enables the development of synthetic IFD architectures, systems designed to replicate the universe's natural folding patterns. By leveraging the high assembly index of DNA, we can build adaptive computing networks and artificial intelligence that natively mimic the recursive dynamics of cosmic evolution. Decoding the mathematical blueprint that folds space dust into biological life gives us the tools to engineer the next tier of the cosmic fractal.